So welcome to the third installment of the Louisiana Coastal Neotectonics Workshop, third workshop. I'm Diana DeLeonardo with the Water Institute of the Gulf, and I'll just sort of give the same introduction that I've given about the purpose of the panel, just in case anyone is new. So the purpose of the panel is to weigh the data, interpretations, and conclusions presented to them by regional scientists in Louisiana during 3 workshops, of which this is the third, to foster open discussion on the role of neotectonics in relative sea level rise and coastal restoration at the planning timescale. These workshops are meant to be a forum for the discussion of neotectonics and its potential impacts on management of coastal natural resources. Next slide. So our panel consists of 3 members. Elizabeth Haycheck from Pennsylvania State University. She is our panel chair. John Anderson from Rice University and David Morig from the University of Texas at Austin. Our panel members are experts in areas of geology relevant to these discussions, such as sea level rise, coastal geomorphology, delta building, geohazard, and seismic interpretation. Next slide. So we'll start off also with the charge to the panel. These are just sort of the general questions that we want them to keep in mind as they listen to all the presentations and as they sort of prepare what they want to sort of summarize for CPRA. So what are the risks temporally and spatially to coastal Louisiana related to subsidence and neotectonics? Are the risks accounted for in existing 50-year coastal management plans? What is the likelihood, if any, of negative impacts due to projects by type? For example, marsh creation is fundamentally different than infrastructure projects. And what are the recommendations from the panel for future research and planning? Next slide. So now I'm just going to turn it over to my colleague, Colleen McHugh, to go over some ground rules and tech check and the agendas for the day.
Great, thanks, Diana. So just a reminder on ground rules and tech check. Please take this moment, if you haven't already, to make sure that you're on mute. Please use the chat box for any questions or comments. And just a reminder that we will be, again, recording this meeting and posting it and sharing that link with you all. So again, this is our third presentation in this sort of third workshop. We'll be hearing today from Dr. Simone Fiaschi, heard yesterday from Dr. Julie Bernier, and on Wednesday from Dr. Frank Tsai. Just a reminder of the process for this. After Dr. Fiaschi's presentation, there'll be time for the panel members to ask questions and discuss the presentation. And then we'll reserve some time at the end for questions that are coming in from the audience. So again, please use that chat box for any questions. And again, a reminder on professional development hours. If you need any additional information on this, please reach out to Diana at her email below or at info@thewaterinstitute.org. So with that, I'll introduce our presenter today, Dr. Simone Fiaschi. He is a postdoctoral fellow at Tulane University, working with Dr. Mead Allison. Dr. Fiaschi's research interests include satellite-based DINSAR to detect and monitor geological hazards. He is currently working with researchers at NASA JPL to advance the use of INSAR techniques in Louisiana for studies of coastal subsidence. He will provide an update to that ongoing work today, and his presentation is using INSAR to measure subsidence in the Mississippi River Delta. So with that, I will stop sharing my screen and turn it over to you, Simone.
Yeah, thank you. Let me share my screen. Okay. I guess you can see my screen now.
Yes.
Okay. So good morning, everyone, and thank you for the introduction. As Colleen said, my name is Simone Fiaschi, and I'm a postdoctoral fellow at Tulane University. I'm working with Professor Mead Ellison from Tulane and Catherine Jones from NASA JPL to this project, which is using INSAR to measure the subsidence in the Mississippi River Delta. So this is how the presentation is structured. So first of all, I will give you some information about the project. Then I will quickly go through the methodology to understand a little bit better how the INSAR technique works and what kind of information you can extract with this technique. And I will show you also some preliminary results over the Greater New Orleans area. And at the end, I will spend a few words about the future work and the conclusions. So this is a postdoctoral project, as you know, that I started just in January this year. So we are at a very early stage of the project. So everything is a work in progress, but still I can show you some of the preliminary results in the next few slides. And the project is funded through CPRA and is part of a larger state federal initiative, which is called Lower Mississippi River Management Program. Probably you already know about this larger project. Anyway, the main objective of the state project is to create an efficient management strategy for the lowermost Mississippi Delta that may result in a sustainable restoration of the wetland ecosystem. Also, one of the main focus is to better understand the subsidence trends in the wetlands, their spatial distribution, what is the relationship with key determining factors such as the sediment compaction, fluid withdrawals, and tectonics. Why subsidence? Because subsidence is one of the most important factors to consider and to take into account into predictive models, in particular if you want to monitor the future coastal conditions. Unfortunately, current knowledge of the subsidence in the lower Mississippi Delta is not very good and derives from many different data sets obtained by different working groups in the last few years. And of course, these data sets are obtained with different techniques. And often the estimated subsidence rates, they differ by several orders of magnitude. So there's still a little bit of confusion about the subsidence rates in the Delta. And the data collected in the last years generally have very limited spatial distribution and high uncertainties. So with this postdoctoral project, we want to test the feasibility of using remote sensing techniques to improve our knowledge of subsidence in the lower Mississippi wetlands. How we are doing that? As you saw from the title, we use the INSAR, which stands for synthetic aperture radar interferometry, and which is a satellite-based technique that can measure ground movements at very high spatial density with millimeter accuracy. Why we use INSAR, not other techniques? First of all, because it's an access system, which means that the satellite emits its own radar beam, so we don't rely on the solar light anymore to image the Earth surface, so we can work in daylight conditions. And also because the radar wave can penetrate to the clouds, we can work in all weather conditions. So we don't care about the cloud coverage or the weather condition at that time we capture the image. Also, the geometric resolution is not dependent on the distance, so we can have a satellite with an orbit of around 800 kilometers, and the ground pixel we can obtain depends on the sensor mounted on the satellite. So we can have a pixel size between 1 meter and tens of meters. And last but not least, it's cost effective. So we can cover very large areas with high spatial density of points and at low cost, because some of the satellites you can use, can be found free online, can be downloaded online for free. And also the software to process this data can be found online. Generally, they are free of charge. Now we are going through a little bit more the technical details. So this is the electromagnetic spectrum. On the left, you have the shorter wavelengths, ultraviolet, visible light, and so on. And moving towards the larger wavelengths, you enter into the radar domain, what we are using with INSAR, which is the microwave domain. Generally, it's between 1 centimeter and 1 meter. Usually, the satellites that are in orbit right now, the INSAR satellites, they work with 3 main bands, which are X, C, and L, and the wavelengths are between 3 and 23 centimeters. And this sketch here is showing you the percentage of transmission with respect to water vapor, depending on the wavelength. So basically, as you know, this is the visible light. We don't have transmission, so we have basically we don't see anything. But once we step into the radar domain, you can see we have 100% of transmission. So basically, this is why we are not we don't care too much about cloud coverage with INSAR. A fundamental aspect to understand is what we call signal backscattering, which is basically how the radar waves that hit the target on the ground bounces back to the receiver. And this backscattering depends on the geometric characteristic of the object on the ground, but also on their dielectric properties, such as the water content. There are three main best scattering mechanisms, which are the volume, the surface, and double bounce. And of course, using different wavelengths or using different bands, they interact differently with the ground. So we see different things in a different way using different bands, just because they interact in a different way depending on the geometric characteristic and the electric properties of the objects. If we take, for example, the surface best scattering mechanism, which is the simplest one, you can see depending on the condition of the soil, we have different kind of energy that is best scattered over the satellite. For example, if the soil is dry, we have a sort of penetration. So basically, part of the energy is dissipated through the soil, but still a good amount of energy goes back to the receiver, to the satellite. But if the soil is wet, this is good for us, for the INSA point of view, because we don't have penetration, so a large amount of energy goes back to the receiver. In the case the soil is too wet, so it gets flooded, or if we have a water surface, a water body such as a river, a lake, or the sea, these surfaces, they act as mirrors. So all the energy is reflected away from the satellite, so we cannot obtain any kind of information from this kind of surfaces. Also, the different bands, they interact differently in respect to vegetation, in particular in respect to the penetration capabilities. So using shorter wavelengths, such as the X band, we stop at the surface of the leaves and the branches because we don't have penetration. But using larger wavelengths, such as the L band, we can penetrate to the main leaves and the smaller branches, and we can hit the main part of the main body of the plant. So we can have a volume best scattering or a double bounce best scattering or a combination of those. Another important factor is the coherence, which is related to the best scattering, but in this case, is how well the best scattering is maintained in time. The coherence goes from 0 to 1, where 0 is basically no signal at all that is maintained, while 1 is perfect, is the best thing we could obtain. And also the coherence, basically higher the coherence means a better best scattering. So also our signal is better, so we can obtain more reliable results over the study area. And of course, since it's a comparison between one image and another image taken in different times, we have basically, for example, in this case, the first image is taken in November, which is called the master image, and the slave image is taken in December. So they are 12 days apart. And as you can see, we have very high coherence. So these are the white parts here, which means that the best scattering is maintained very well in this time period. This is basically the New Orleans area and the Mississippi River. So the delta, this is the Mississippi, and New Orleans is here. So basically, where we have buildings, structure, or solid object, basically the coherence is always high. But also in this case, since we are just 12 days apart and we are in winter time, also the coherence is maintained over the wetlands. If we move forward in time, so with the same master image with a different slave, in this case 36 days apart, as you can see, the coherence is very high still in the city. And we are starting to lose some information over the wetlands. Moving again, 60 days, still very high over New Orleans, and lower and lower is getting lower over the wetlands. 84 days, we completely lost almost all the information on the wetlands. 180 days, similar situation. And if we go at 120 days, we lose completely all the coherence and so all the information on the wetlands. We have only coherence and data over the New Orleans area and some along the river, the Mississippi, because we have some buildings, some structure, and also a secondary canal here. So as you can imagine, coherence is a very important parameter to consider and to take into account when you process INSAR data, in particular the vegetated areas, because of course it affects your results. So how the images are acquired? Basically, we have one satellite that has one orbit, or ascending or descending. And the orbit is around between 700 and 800 kilometers. And the images are acquired not just straight forward the satellite, but with a particular angle, which is called line of sight. So we have the first acquisition at T1 over our study area. It can be, in this case, the small building. And if we acquire another image over the same area, but at different times, can be few days apart or 1 month or 1 year apart, and our object has moved, we can compare the phase between these two images. So we have a phase shift, and we can translate, we can calculate from this phase shift the displacement of the objects. So when you acquire a side image, what you obtain is the intensity map, which is the same as backscattering. So you have all the energy, how much energy is reflected towards the satellite. So you have a very nice picture of what are the features on the ground. And then you have your interferogram, which is the phase comparison between the two images, which looks like something like that. And you have these nice color cycles, which are called fringes. And basically, this is a representation in terms of phase shift of the displacement occurred in this area between this period, so between August and September 1999. And this shift and this displacement is caused by, in this case, by the an earthquake that occurred in Turkey between these two dates. So basically, knowing that what band we are using, in this case a C band, and counting the number of fringes, you can calculate the maximum displacement of this area here at the epicenter of the earthquake where you have the fault line. So basically, the first fringe is zero displacement. You can count 2 fringes, so you have 5.6 centimeters, and then at the center you have 22 fringes, which correspond to 60 centimeters of displacement, which is the maximum rate of movement we had between August and September 1999 because of the earthquake. If we acquire a lot of images with time, so we have, let's say, 100 images over 3-4 years, of course, we can obtain a lot of different interferograms. And if we stack them together using multi-temporal instant technique, at the end, we can perform a time series analysis. So you have, for each of your pixels, you have the displacement information in space and time, which is what we aim to have in all our studies. So what we can measure with INSAR. As you understood, with INSAR we can measure just surface movements. So we don't have any sort of information about the underground movements, but just the response of these all the different factors and their response at the surface. And these movements are relative to a reference point, and we choose the reference point generally as a point that doesn't have any movement, so it's a stable point, and is over a very coherent area. So basically, our signal is good in that area. Or you can choose a stable point with known velocity, so for example, over a GPS station, so you can correct your INSAR results in respect to the differ with the data acquired from the GPS. So basically, with INSAR, you can measure, for example, subsidence related to setting and compaction, movement related to water level changes, and of course, on wetlands in this case, accumulation of vegetation, oxidation of organic material, the exploitation of recharge of the aquifer, so both uplift and subsidence, tectonic movement, or deformation of buildings, or more often a combination of different factors. So as you can imagine, having a particular INSAR signal in an area is very difficult to understand what's going on and what is causing that signal. So we usually need some ground information to validate our results and to untangle what are the main factors contributing to the signal we see. There are only a few previous works that applied INSAR over the New Orleans area, and none of them applied over the wetlands using multitemporal images. The first work was done by Dixon et al. In 2006, published in Nature, and he used 33 RADARSAT images, which is a Canadian C-band satellite, and he covered 3 years. So he has 3 years of data from 2002 to 2005. And he found some subsidence, of course, over the New Orleans area with a mean value of around 6 millimeters per year. But there are some spots, in particular, in the northeastern here, in the Michoud area, and also along near the international airport, with values around 2 centimeters per year. And also more interesting is the subsidence along the Emergio Canal, which is just very close to the levee, to the floodwall here, and he found subsidence rates up to 25 millimeters or 2 centimeters per year. As you can see, the results are quite patchy, and this is because in 2006, the INSAR technique, the process technique, and also the data, they were at the early stage, so probably there is a high level of uncertainty related to these measurements. More recent work was carried out by Kathleen Jones, our collaborator for NASA JPL, published in 2016. And she analyzed just 2 images, so it's not a multi-temporal insert, but she compared 2 images, one acquired in 2009 and one in 2012. They are coming from this UAVSat airborne system, which was developed by NASA, which is an L-band, which mounts L-band system. And in this case, the pixel size, the resolution is much higher. It's around 5 or 6 meters. And also, she found some spots over the New Orleans area where there are higher rates of subsidence. In particular, again, over the Michoud area where we have the major GPS station, and also other spots here and also here. And most of the subsidence related to industrial activities in the area. Also, in this case, there are some uncertainties, in particular along the lake. We can see she found uplift and the white pixels here. And this is probably not real, so it's related to the error related to the technique. So with this project, we want to make some advances in respect to previous studies. And we are going to use the most advanced satellite we have available right now, which is the Sentinel-1 constellation. So it's a constellation of 2 satellites developed by ESA and launched by ESA. The first satellite in 2014 and the second one in 2016. And the main advantage of this satellite is that, first of all, it has global coverage, and depending on the area, of course, we have a better coverage, for example, over Europe, because we have a combination. We can use both satellites working together, so we have a revisit time, which is the time span between one acquisition and the other of 6 days. In the other part of the world, such as in our study area, we have just 1 satellite and 1 track, the ascending one. And we have images every 12 days. The maximum resolution of the satellite is around 20 meters, which is quite good. And also another advantage is that the data can be obtained for free. So you can go in different portals, such as the ASF in this case. You choose your study area, you can download the data for free, not just SAR data. There are many different Sentinel missions. So Sentinel-1 is for SAR data. There is optical data, multispectral. So depending on what the needs of your project, you can download this data for free. And this is an example of the data coverage over the New Orleans area. And in this case, we have 110 images. This is few months ago. Right now, we have more images because they are continuously acquired every 12 days in this area. Another advantage is that we can cover a very large area with just 1 image, because each image is huge. So we can cover around 250 kilometers by 180. And as you can see, the image is split in 3 parts, which are called SWOTs. And for this preliminary test case, let's say, for this part of the project, we are focusing on the central SWOT, the central part, which is covering the Greater New Orleans area and the wetlands. But in particular, we are focusing on the urban area of New Orleans, because it is a much easier target for the insert processing point of view. Because, as I said, we have very high coherence, so probably the results can be obtained more easily, and we have better results than the southern part. We have just wetlands. So the next steps will be to focus on the wetlands, which is a more challenging environment because we have a lot of superficial water. We have vegetation, which changes with the season. Also, we have flooded surface, which we change position in time. So we have different flooded areas in different times. About the results, we have, as I said, we used a little bit more than 100 images covering 4 years between February 2016 to February 2020. All these images, which are the yellow dots you can see here, are connected to each other 5 times, which are the blue lines, which are the interferograms. So at the end, we have more than 500 interferograms. And in this case, the interferograms are color-coded based on the spatial coherence. So just to have an idea what is the coherence between one image and the other. In this case, for this process, I didn't use the full resolution of the satellite, but I increased a little bit more the pixel size at about 60 by 60 meters. Because it helps during the processing to have smoother results and also to maintain higher coherence over in particular over the vegetated areas of the study area. But still, 60 meters are quite a good pixel size because you can still capture relatively smaller objects such as the buildings and the levees. On the right, you have the total temporal coherence obtained over the New Orleans area with a slightly different color scale in respect to the previous slides. So in this case, red is very good coherence, and blue, our dark blue, is basically zero coherence. And as you can see, as we expecting, we have very high coherence over the city, and over the wetlands. Basically, we have very low coherence, so we cannot obtain any sort of useful information over these areas. Still, we could obtain higher coherence or pixel with higher coherence up to 0.4, 0.5 in the wetlands, in particular the one protected by the flood walls and the levees. For example, in this area here. And if we compare this information with the land cover database, you can see we have that these areas are classified as wetlands, in particular as woody wetlands. Sorry, herbaceous wetlands in this case. And we have very high coherence in this area, probably because this part of wetland it doesn't get flooded. And in fact, if you move just a little bit north of this area, you have more superficial water and probably more flooded surfaces. So as you can see, we could, the coherence here is much lower. And also higher coherence we found along the Mississippi itself, where we have some grassland, what is classified as grassland, and also some smaller villages and small buildings, and also along the secondary canal here, where we have more woody wetlands and other smaller buildings. At the end, what we have as results with INSAR is a velocity map, or can be also a displacement map. But in this case, I'm showing you the mean velocity map for the total period in millimeters per year. So each of these points has a velocity value and also a displacement value, so you can extract the time series. And in this case, the velocities are color coded based on the value. So in blue, you have the positive values, which means generally uplift, which are the points moving towards the satellite. In green, you have the stable length, more or less around the pixel with the velocity around ±2 millimeters per year. And in orange, red, and purple, you have negative values, which means subsidence, and other points moving far from the satellite. All these measurements are relative to one reference point, which is taken here, where you can see the red star. And we choose this point because it's a higher coherent target, and also because here we have a GPS station. And this GPS station is showing basically very little movement, so it's a good point to choose as reference. In total, we found more than 113,000 points, with a mean point density of around 40 points per square kilometer, which is quite good, but it was expected because we are working over the urban areas. This is the histogram of distribution of velocities. So as you can see, we have a Gaussian distribution. So part of these, the velocity we found are related to the noise, or to the, let's say, the error related to the technique. In particular, the one around ±2 millimeters per year are what we consider a stable length, which is a quite conservative value, because the error we measure with the processing software is around 0.7 millimeter or 1 millimeter per year. So I just increased the stable length just to be more conservative, and knowing also what kind of error we can get with this satellite. Anyway, as I said, we have a sort of Gaussian distribution of the velocity. So part of these values are related to the noise, but some of them are also real values, because you can see there is a skew of this curve towards the subsidence values. And also some of the uplift values are also real. I will show you why later on. So comparing our INSAR results with the land cover is basically what we saw before. And I've extracted the number of points, the total number of points falling in each category. So we were expecting very high points over the urban areas, but also we found a lot of points, around 50,000 points just over the vegetated land, in particular the wetlands, the woody and herbaceous ones. And the value you can see here are the maximum subsidence found in each category. And if you don't consider the urban areas, because the high values here are related to industrial activities, we found that most of the higher subsidence value are over the wetlands, and in particular over the herbaceous one in this area here. So as I said before, we need a sort of validation of our results because we are working with satellites and also because everything is relative to a reference point. So in this case, I've compared, well, first of all, as I said, this is a work in progress. So I'm still gathering all the information we have available in the area, such as the geological map, the geomorphological map, land use, as you saw, and other measurement we could have available and that can be used as for validation of our results. In this case, I'm showing you the comparison between our results and the GPS station that I have found in the area. And they are, and these data are from the Nevada Geotechnical Laboratory. So in total, we have 5 GPS stations, and in this case, the INRI one was used as a reference. So as I said, the INRI GPS station basically is a very good point to choose as reference because in the total period, it shows a mean subsidence values around 1.3 millimeters per year. I think the total period is around 8 or 9 years. But if you take into account just the period overlapping with the INSAR results, you can see the movement is around just 0.4 millimeters per year. Basically, it's a stable point. The comparison between our INSAR results and GPS data is quite good. And we are quite happy about this comparison because, as you can see, the difference is less than 1 millimeter per year generally. So everything is in the range of the error of the INSAR approach we are using. The only big difference we see is that, between the ENG5 GPS station and the INSAR points around that station. So the INSAR sees uplift of around 1 millimeter per year, while the station shows subsidence of 1.4 millimeters per year. And in particular, the difference is mostly in the last part at the end of the time series where we have uplift. We see uplift, and this starts more or less in August 2019. Probably we could explain this behavior because the ENG5 station is located here. As you can see, it's very close to a wetland. And over with this wetland, we see uplift with INSAR, probably because we measure all water level changes or the vertical accretion of the wetland itself, or a combination of these two factors. So basically with INSAR, we capture part of this uplift related to the wetland. And of course, this is not captured by the GPS station because it's mounted over a building or a stable object. So basically, probably this difference related to this, what is the different target of of the two approaches. And also, as you can see, we have a sort of cyclical movement of our INSAR time series. So we have uplift for a period, we have strong subsidence and uplift again. And so probably this can be explained as movement of the wetland. Another interesting point to spend a few words is that, I don't know if you remember from the previous works that the Michoud area here was showing quite high rates of subsidence, up to 2-3 centimeters per year. But what you can see here is blue points, so which means uplift, which is quite strange because usually we don't expect uplift in an urban environment. But both INSAR and the GPS station, they show uplift in the area with basically the same values. So 3.1 millimeters for the GPS station, 3.5 millimeters for the INSAR. I just found some information online, and basically here there is a power plant which was pumping a lot of groundwater to make the power plant functional. So this was the main source of the subsidence in the area. But starting from June to 2016, they starting to stop the pumping activity. So the power plant was decommissioned, and starting from this point or a little bit earlier, we see a recovery of the aquifer. So basically, we see the uplift with both GPS and the INSAR, which is quite interesting. So this gives you an idea what kind of information we can see with INSAR, both spatially and temporally. Sorry, I just have some water. Part of this the subsidence signal is very localized. And in particular, most of these subsidence values are related to industrial activities in the area. I have here just 4 examples. In this case, you can see this is the New Orleans Airport, where the maximum values are around 2-3 centimeters per year, or just over the newly built terminal. In this case, you have the River Birch gas plant. You can see a quite strong subsidence, very, very localized in a field. In this position here, this is another industrial site. I couldn't find any sort of information over what kind of activity they are doing there. But of course, all the subsidence points are over the building. So basically everything is related to this, the activity they are doing in this area. And in this case, it's a little bit different. This is a landfill and junkyard. So basically they are piling up stuff. I think there are cars. So basically they are putting more load over the ground, and we are capturing the overload in terms of subsidence. Probably more interesting for you is also the subsidence affecting the wetlands. So right now we are focusing on the eastern part. This is the Mississippi River Gulf Outlet, the MRGO, which runs just parallel to the flood wall, which is this one. And as you can see, we found a lot of insert points over the wetland, in particular in this lower part here, which showing very high rates of subsidence, up to 4 centimeters per year. In particular, where we have this canal that is going basically towards the lake and towards the outer part of the wetland. Also, as you can see, we found a lot of points over the flood wall, and I've extracted all the points with a buffer of around 100 meters over the flood wall itself. And as you can see, the velocities are not uniform, so they vary depending on the position. Basically, there are a few spots where we have an acceleration of the velocities. In particular, there are 3 main areas, which are here. Sorry, in this case, I've extracted all the points along the levee, the flood wall. So here you have around 25, 24 millimeters per year of velocity. Here you have a maximum subsidence value of around 32 millimeters per year, which is located in this spot here near the canal. And at the end also there is another acceleration of the subsidence values around 3 centimeters per year. So as you can see, INSAR can provide you some user information about spatial and temporal information about the subsidence or the movement affecting also infrastructures such as the flood walls and levees. And also this information could be useful for the engineers or the one in charge to control the functional how the levee itself is functioning. So if there should be probably we can point out some areas where the control should be focused, because maybe these areas are more critical from the stability of the levee itself, or maybe there is some damage or any other problem to the levee. Similar approach on the western side. So we are over another wetland protected by this flood wall. Also in this case, we found a lot of information on the wetland itself. We have some uplift in this area, probably, as I said before, related to the water level changes or vertical correction on the wetland itself. But in this case, in this area here, we have mostly subsidence up to 2 centimeters per year, where we have the yellow points. But moving from the inland towards the outer part of the wetland, the subsidence seems to be increasing. Also in this case, the flood wall seems to be affected by subsidence value, quite high subsidence value, which are again not uniform, not constant all over the levee itself. And in this case, there are 4 main areas with an acceleration of the movements, in particular this spot here, and the maximum values are here at about 28 millimeters per year, and also here same values. But also there are some areas where we don't have movement, so we have stable land, in particular this spot here, and also moving from the outer parts of the wetland towards the inner parts. So you can see we are moving from the very high subsidence values toward stable land, basically. So again, also in this case, the INSAR data can be used to point out which area can be more critical and where the engineers should focus their attention when they monitor the levee or they control how the levee is functioning. So basically about the results, this is a little bit more or less I'm done. About the future work, so we want to refine, as I said, the current results over the Greater New Orleans area. And also we want to validate, of course, our results, have some sort of interpretation. Because so far we are just focusing on obtaining some results, and we didn't have too much time to interpret what we saw with INSAR. Most of the future work will be focusing on the wetlands, so using INSAR to monitor the wetland area. So we want to adopt ad hoc INSAR processing techniques and strategies for this kind of terrain, because as I said, it's more challenging. About the conclusion, so our INSAR approach allowed us to examine the more recent subsidence trends in New Orleans with the lower uncertainties in respect to previous studies. And our results confirm that in the urban areas, the higher subsidence rates are basically can be attributed to the industrial activities. And differently from the previous work, in particular Catherine Jones et al. 2016, the Michoud area shows not subsidence, but uplift. And we saw that there's a clear connection with the aquifer recovery after they stopped the activity of the power plant. Also, the Levy flow system shows areas with high subsidence rates up to 3 centimeters per year, in particular in the eastern side of the city along the MRGO canal, as previously described by Dixon et al. 2006. And also in this study, we were able to measure INSAR points or have surface movements not only on the city, but also on the wetlands, particularly the one protected by the levees and close to the urban areas. Some of these wetlands show subsidence rates between 2 and 4 centimeters per year, in particular in the central wetland unit, while others they show uplift up to 2 centimeters per year. We are not sure why we see uplift, but we could explain this with the water level changes or the wetland accretion. So with this study or with these preliminary results, we demonstrate the feasibility of using a satellite-based INSAR approach to detect and monitor surface movements not only in the urban environment, but also over the wetlands in the greater New Orleans area. And this approach can, of course, can be used in a very efficient way to monitor the levee and flood wall system. And as I said, the next challenge would be to extend our INSAR analysis over the lower Mississippi wetlands and define the best data processing strategies in such areas. So I'm done, so thank you for your attention, and I'm glad to answer to all your questions.
Thank you so much, Simone. We'll turn it over to the panel now to ask questions. John, can we start with you?
Sure. Well, first of all, very, very interesting.
Thank you.
Thanks very much for joining us. I guess the first question I have is, do you have I assume in your analysis, especially around Lake Pontchartrain, that you have a fairly, how much information do you have on surface faults in that area? Are you looking at those?
Faults?
Yes.
Actually, as I said, we are trying right now to collect all the information we have and to have a better understanding of what's going on in the area. I think that the faults, as I saw from previous work, the movement of the faults is very, very low. So we are just 1 millimeter per year movement or less. So basically this is within the area of the techniques. Probably you can have some information about the fault, but this is basically just is blending the noise or the background noise of the technique. So probably we could not distinguish between the fault movement and the other superficial movement we have in the area.
Okay.
Just because the movements are so subtle.
Yeah. Another, I guess, just point of interest. I was very interested to see that you were actually seeing some rebound in the area where the power plant had stopped using groundwater. I thought that was very interesting because in Texas, we have an example of a high subsidence up in the sort of northern part of Galveston Bay that goes back to the late 60s and early 70s when they were using a lot of groundwater for industrial purposes. There was a couple of meters of subsidence actually in the area around Johnson Space Center. To my knowledge, and there has been no rebound. Now, this may change. Maybe we need to look at some INSAR data there as well. Yeah. So I was sitting here in my own mind trying to rationalize what was different geologically about the aquifers in these two areas that we might learn from about, how aquifers respond when you deplete them and then when you allow them to recharge. My guess is it has something to do with the depth of the aquifer, that a shallower aquifer is going to recover much faster than a deeper one. But I think it'd be very interesting to look at that. I'm gonna see if I can pull up some information on that later for the panel.
Yep.
My last question or observation has to do with the levee, which I think is really cool. The correlation of the levee in the areas of subsidence. And this is obviously going to be an extraordinarily valuable use for these data. I thought it was very interesting that it's almost like a wave-like character to where you see high substance, low substance. And I'm wondering if you had any chance, and I know you're in very preliminary stages here, but you know, let's assume, though it is random, that there is no reason I can think of why there would be any kind of waveform there. One would think that the best explanation for that would be subsidence, shallow subsidence related to just compaction, especially since you're building a levee there. And I would also think that the Corps of Engineers would have I know they have platform borings. We saw some yesterday along those levees that measure the thickness of the Holocene section. I'm wondering if you have had an opportunity to look at those data to compare the thickness of the Holocene section to the degree of compaction.
No, I mean, we have some data about the levees, how they are built, and also some leveling of the height of the levee in different times that were provided by the engineer corps. But yeah, well, I'm still looking to this kind of data, but no, I didn't compare the ground information with of the levee. But I think, as you said, the subsidence can be related to the compaction of the levee itself, because they are putting more material over it, because they are basically repairing or they're increasing the height of the levee in some spots, so that can be a possibility. And also, you have to consider that the pixel size is around 60 meters. So I'm not quite sure right now if the pixel is capturing just the levee itself or also the wetland near the levee. So part of the signal can be related to the movement of wetland itself. So we had to figure out why. So what are the source of contributions to this subsidence?
Yeah. Well, again, we saw at least a figure yesterday that showed a map that shows some good examples of not necessarily in this area, but I'm sure they must exist, where they had very closely spaced borings. And so
anyway, we are going to check all the data we have available in the area and try to have some interpretation of our results.
Yeah, I guess the other thing might be that there might be some construction differences in the material used or something of that sort. Again, I'm sure the Corps of Engineers would have that information, but to me, it seems like that'd be a really important next step here, is to try to figure out why these variations exist. In terms of planning for future construction or repair of the levee systems. So, but very good talk. I really enjoyed it, and clearly I think INSAR is going to be an extremely valuable, provide some extremely valuable information that's going to help us move forward in terms of not only mapping out these effects, but starting to really get an understanding, because we're really starting to get this kind of spatial distribution that we need to really get at the fundamental problems of what's causing these more localized variations in substance, especially. So thank you very much, and I'll turn it over to the next panelist.
Yeah, you're welcome.
Hey, this is Mike Miner. John, I wanted to give you. There's a unique situation over there in the Mr. Go area, and I did some work over there, and the deal is the Mr. Go was authorized as a navigation channel before the hurricane protection system. And so that the spoil bank, it was a dredge spoil, so they dig the canal and they pile it up on the side. That became where they decided to build a levee. And so they built a levee out of dredge material, and they also had to import some. But there's a nice line of borings that goes down to Mr. Go that were used for design, and then somewhere that were used that were taken post-Katrina, but those design borings were part of a report done by Kolb and Van Lopik, and they mapped the inner distributary unit is a high water content clay, and it varies along that reach of that levee, and the thickness correlates to the rates of subsidence you see along the levee. And another interesting thing is there's the dredging records showed that the maintenance dredging was extremely high along those same reaches. So what was happening is, as they piled the material onto the levee, it was being squeezed out back into the excavation. And also, which was pretty cool, is on the dry side of the levee, there's a borrow pit, and there's mud lumps in there. So mud dye appears. So it has to do with a kind of a unique situation at that setting, and it is because of the geology.
Yeah, one would think so. Yeah, I just was particularly interested in what looked like that sort of uniform spacing, almost waveform. That would almost imply some engineering kind of, I mean, there obviously wouldn't be a geological explanation for that. If it's a real pattern, it looked like it in your graphs, then that would almost imply that there was some sort of engineering pattern there where they might have used different materials as you went from one area to the next, or there might have been differences in the height of the levee, something of that sort. That was the nature of my question.
Yeah, it is geologic. It's the thickness of that interdistributary deposit that varies along there.
Yeah, thank you, Mike. That explains it. Yeah.
Thanks.
Yes.
That's all I had.
Awesome, thanks. I'll make sure I'm unmuted here. Thanks, Simone. That was really great. And like John too, this is it's exciting to see, and I can see the potential. But perhaps you can help me temper my expectations. I think one of the things that I think we've seen over and over again is that the wetlands are areas of great uncertainty, and so I guess I'm wondering if you could talk a little bit about kind of how tractable it is to expand some of these techniques into the more wetland areas that are away from some of the urban infrastructure, and if that's possible, what would be needed to do that, and how hopeful might I be about this?
Yeah, that's the main part of my project actually. So I've done few try to work on the wetlands. It's really tough because it's from the inside point of view, we have the main problem is water. It's not even vegetation, but it's water. Okay. And the problem is that the different part of the wetland get flooded different times. So we basically, once you have one pixel or few pixels that lose coherence or gets flooded, you lose the entire time series. So you cannot obtain information over that pixel.
And is that just to clarify, because you need the full time series. If something is flooded and then emerges later,
yeah, I lose completely that point.
You can't. Yeah. Okay.
Yeah. So I've done a few tries. For example, you can still see my screen, right? I guess.
Yes. Yep.
To adopt some different techniques to adjust my parameters. For example, this is the normal results you saw before. So using the full stack of images, and you can see there's no coherence at all, so we cannot obtain any information here. But just using the winter times, for example, from November to March, this improves the overall coherence, so you can still have some information. So there is some sort of hope in the process point of view. And also in this case, I've increased the pixel size because a larger pixel size helps in maintaining. So you average more in the area, so it helps maintain the coherence with time. The problem, for example, here in winter time is that all your images must be connected to each other in the best possible way. So having just winter dates, we have just cluster images which are not really well connected to each other. So this is another problem, and maybe the errors related to this approach are much higher than before. And also, generally, using more images is better than using few images, of course, as you can imagine.
Yeah.
So there is some hope, I guess, but it's really tough. And probably a better approach to use a different satellite. For example, using L-band, you can maintain higher coherence because you have more penetration capabilities in respect to vegetation. So you can hit the ground, if I can say the ground of the wetland, or the main part of the wetland. and it may help. The problem with L-band is that data sets now, I think they are not free, so you have to buy them, and the coverage is not great. So we have to check if this is a road is worth trying or not.
Yeah, it sort of depends on data availability and cost, I guess.
Sure. Yeah.
And then, so one other question, and that's actually really nice to see that the winter dates, the coherence associated with that, and it's very patchy. I guess, and just so my understanding is that the sort of patchiness there, each of the uncertainty associated with each point or each grid cell is sort of independent of its neighbors. Is that true, or am I thinking about that the right way?
Yeah, that's more or less true. Yeah, because each pixel has its own coherence, its own phase, that is best scattered. So basically, yeah, each pixel is independent to each other.
So even if you have patchy coverages, the areas where you have coherence should give you a legit, or I guess the uncertainty is, I guess the question is about uncertainty when it comes to that.
Generally it's better if all your image is connected. So all your points are connected to each other. So if you have a phase island, this is difficult to process the phase island just because it acts as an island. So you don't know what is the relationship with the rest of your study area.
Gotcha.
But there are some approaches that can make sort of bridging this difference. Answer to your question, they are independent to each other, but it's better if they're connected. And so, if you have a patch of land that shows coherence is detached from the rest, you can still have some information, but probably the error is more high than the rest of the study area.
Yeah, and then another question about that, the winter coherence map, and maybe you haven't had a chance to look into this yet. I'm curious if what the attributes are of the areas that you are getting better coherence. Are those?
It's a good question. I don't know actually. I think it's related to the height of the wetland or what kind of vegetation we have.
Okay.
So basically, probably this part of the wetland which maintain higher coherence are basically more stable from the flooding point of view. So they don't get flooded too much. For example, in winter time in this case.
Okay.
So probably here you have more superficial water, so it's or it's a different vegetation, so they act differently in respect to the wet season or the dry season. Okay. But if you take for example, the land cover classification, they are classified as the same wetland, the same type of wetland. So probably I need to find more specific information about the type of plants or association in those areas.
Or maybe the local elevation. Or
exactly. Yeah.
And then I guess, can you give me a sense of, when you talk about more or less uncertainty, sort of when you start either using different bands or with this kind of patchier coverage that we might, and in the best case scenario, I guess the wetlands are going to be patchy probably, right?
Yeah.
Like, what is the differences in sort of uncertainty in terms of the subsidence or uplift rates that you would feel comfortable, or do you have any sense of
using different bands, you mean? Different satellites? Or?
Different bands, and then also the difference between sort of the certainty you have with the very high, like a big area with high coherence versus these sort of patchier areas.
So it's another good question. The problem with INSA is that you're not always sure what are the error related to your technique if you don't validate your results with a leveling or GPS station. Okay. And usually what we have with the Sentinel satellite in urban environments or perfect condition, the error is around, let's say, 1.5 millimeters per year, plus minus. Probably in the wetlands, this is related to coherence, so probably a little bit higher, let's say double it or triple it, so I don't know, half centimeters of error. But you never know because you have to validate your results. What is calculated from the software is you have an idea, but it's related to the distance from the reference point and from the coherence. For example, the software calculates a mean error in the previous work around 0.7 millimeters per year, which I don't think it's real. So this is why I choose like plus minus 2, because I know from previous work that this is the range of error we have with the technique. Okay. Unfortunately, I don't have some numbers to give you because it's very relative to each pixel and to the different condition of each pixel. So it's very tough for me to give you some numbers, but probably
that makes sense.
Probably between 2 in the wetland, between 2 millimeters and 5 millimeters per year of error, if I'm lucky.
Yeah, good. No, thanks. I appreciate your perspective on that. So cool. Colleen, I'll turn it over to David now.
Yeah, thank you for the presentation. And I'm gonna, I think, build on both what what John and Liz asked. I'm going to start with thinking about the tool and understanding what it can do and not do. And first, I mean, coherence, I mean, what exactly goes into your coherence formula?
Basically is the, let me see. Basically is the sum up of all the contribution of the backscattering in my pixel. So basically it's a complex number. You have the real and imaginary part of the image. And if you sum up, it's a random sum up. And if it's positive, it's positive coherence, so it maintains coherence. If it's negative, basically you don't have coherence. So it's basically a mathematical approach that measures the backscattering.
So it's telling you something about backscattering, and then the question is, you know, given your intuition. So like here, when I look at this plot that you just put up there, you also showed us like a histogram of calculated displacement values in one of in a later slide.
Yes.
What was
here? I mean.
No, it was a hit. Yeah, we're getting there.
In the results, okay.
Yeah, I think it was like sort of the error histogram.
Yeah. It's not even an error. Yeah, it's
a distribution of velocities. Yeah.
It is the distribution, right? So it's not error per se. No. Interpreting some of it is error, but it's just the distribution.
Yep.
So is this associated? What kind of coherence value is this associated with? This particular.
Basically, in this case, it's independent from the coherence. It's not an error histogram. It's just the velocity, so it's what is calculated by the.
Right, but is this for that whole map?
Yeah, it's the total point. So you have the count here, and you have the velocity. So
okay, and so have you ever looked in areas of different coherence to see really how these distributions parse out? You know?
Not in this case, but yeah, this is something you usually do for the next step of the process here. Because right now I want to just to.
And so when does it become, so you must have a way to know at what coherence value this tool gets really uncertain, right?
Yeah, basically.
So what coherence value is it?
In this case, we masked everything. The coherence we masked is everything less than 0.2. Which is quite low, but this was necessary to obtain some information on the wetlands and the levees.
Mm-hmm.
Of course, having a lower coherence means higher uncertainties.
Right.
I don't have the numbers here.
Okay.
Probably is everything is related to the coherence. The better the coherence, the stronger the signal by scattering, so the better the results in terms of error you can have. So basically, this is not, I don't know if I answer your question or.
I was wondering if I could quickly get to a way to get a sense of how likely this is going to work in the wetlands.
Yeah.
Because it seems like you already actually have the data. You know, if you filtered this and just looked at the coherence between values between like 0.4 and 0.2 and looked at what the distribution is, you'd have a pretty good sense of because a lot of that distribution you show us is associated with extremely high coherence on buildings.
Yeah, that's true.
And so it does seem that right away we should get a pretty good sense of how this will work on the wetlands. So that's pretty interesting.
Yeah, for example, if I choose like 0.3, 0.4 of coherence, you lose this point over the levee. Since I wanted to show you some information on the levee, also here, I just reduced the threshold itself. But for example, here on the wetland, I think it's 0.4, 0.5, the coherence, so it's pretty high. It's pretty good, just because it's protected by the floodwall itself. And again, here, I mean, it's basically zero, so you can obtain any sort of information. Or you can obtain information with very, very high uncertainties, which is not the best thing we can get.
Does it matter whether the surface is wet or dry? And between time? Like whether the vegetation is dry.
It can matter. Yeah, everything related to the geometry of the of the object and the how wet it is, it may affect the best scattering and also the coherence. So also the height of the plants. If they are too high, probably you have a different best scattering because you cannot penetrate with the seabed the total height of the plants. So you cannot hit the water surface or the land. Or if the leaves are too big, you cannot penetrate them. So it depends on everything you have on the ground, on the surface.
So let me flip it then. Now that we have this tool and it's becoming more and more available. We've had the tool for a while, but now that this data is becoming more and more available, what would you like to see built in the wetlands to actually benchmark a tool like this? I mean, if you were going to say, this is what I need you to build me so that I have confidence that this is working in the wetlands, what would you have constructed?
Yeah, usually they use what they call corner reflectors, which are structures of big, like 1 meter by 1 meter. It's like the sort of half cube, which is cutted, which is pointed towards the satellite. So basically there you obtain very high coherence all the time, perfect coherence, because it's made to reflect the insert signal. Basically, for example, in Italy, I come from Italy, and in Venice, in the lagoon, they planted like 50, 100 of this corner reflector to obtain information of the wetland. The problem is that it depends where the corner reflector is anchored. If it's too low, you just obtain information over the lower part of the subsidence. You have subsidence.
Right.
So the best thing is to have something, let's say, stable, but at the surface.
Yeah. I
don't know if it's possible from the geotechnical point of view, but usually you can do that. So something that it doesn't change the position, the XY position, but just the Z one. So a corner reflector is the best thing and the cheapest thing you can build over the wetland, probably, to obtain reliable results over this kind of vegetation.
Great. Thank you.
You're welcome.
That's it for me right now.
John or Liz, any follow-up questions or comments?
Yeah, I had one comment, and that is that, yeah, I agree with what all Dave's concerns and Liz's concerns. I do think that one of the things that we can be optimistic about is we've heard over the last several months that sort of different perspectives on the causes of subsidence. One being the Tornquist school, who argue that shallow subsidence related to the thickness of or compactable Holocene sediments is the primary culprit. We've heard yesterday that oil and gas extraction is the primary culprit, and we're going to have to deal with this as a panel. We're going to have to sort of weigh these two. It seems that this approach, even though it may not give us the resolution we would like in terms of the magnitude of substance, it's going to provide much better spatial control on substance. So when I express optimism about this method, I guess my mind sort of moves towards thinking more about the controls and how we might get at some of these questions. The other question I had, though, has to do with LIDAR, and particularly in the Pontchartrain area here, which of course measures some of the same sort of backscattering kind of parameters that you're measuring and dealing with. And I'm wondering I assume there is LIDAR data for this area, and if so, can that data help with trying to get at some of these issues that you just talked about in responding to Dave's questions?
Yeah, there are LIDAR data over the area. We can use LIDAR data to, basically when you have the insert signal, you have to remove all the contribution for the topography and the atmospheric contribution also. Even if we penetrate the clouds, we still have to remove some of the delay related to the water vapor. And about topography, usually, since you have a stereoscopic view of the satellite, you have some of the signal is related to the height of your ground. So basically, I use generally the SRTM DM to remove the topography, but of course, having a better DM, much preciser DM, such as the LiDAR, helps in filtering more the phase and having a more smoother results. And also probably it can help to know the height of the wetland, as Liz said, so to have some sort of interpretation why we have some coherence in some spots and why we don't have coherence in some other areas, because of maybe the vegetation is higher or the wetland is higher. So probably it can help in that sense to interpret better our results. Don't know if it answer your question, but yeah.
Yeah, I'm just sort of, this question sort of came to mind in response to one of Dave's questions that had to do with benchmarks.
Yeah.
And I'm wondering if the best approach is to actually use physical benchmarks, or to have, you know, sort of maybe specific areas where you had LiDAR coverage on an annual, semi-annual basis, for example, might be another approach to getting some of these baseline data that you need for calibration. Yeah,
probably flying a LiDAR every few years is kind of expensive, consider the extent of the area. And we have some GPS station also along the Mississippi and some part of the wetland that we can compare our results with. So probably that may help in benchmarking our results. Yeah, but you're right. If having just a LiDAR data every year would be perfect. So you can have
and I'm not sure you'd have to cover the whole area. I mean, if we were really
maybe some spots,
yeah. I mean, you could actually pick key areas that might be representative, high substance, low substance, you know, various types of substance, and maybe I have some isolated areas where you could scale down to you know, smaller sort of areas that are used for specifically for calibration, not trying to cover the whole area.
Yeah, I was thinking that if you want to compare DSMs made from LiDAR data, that can be also a problem, because LiDAR data, I think they have a resolution, vertical accuracy of around 10 centimeters, 14 centimeters. So, you know, we are talking about millimeters per year here. So the error related to the LiDAR approach is much higher than our data. So you can use them as general benchmark if you have a long-term series with many different LiDARs with the years. Just comparing 2-3 years probably is not. I'm just thinking it's not helping, but yeah, it can be used for other different things for the interpretation, for example.
That's all I had. Thank you.
Can I ask one other question about, since you mentioned the comparative errors of LiDAR and INSAR?
Yep.
And you were talking about how the advantage of INSAR is that you don't need to worry about atmospheric conditions too much. But is that true? I mean, radar is absorbed. I mean, water vapor does affect radar. Yeah. So it can't be just the fact, you know, and we know that. We'd use radar for all sorts of things otherwise, like they do on Mars and various places where they don't have water vapor in the atmosphere. So there, it can't be quite as simple as this plot says.
Yeah, that's true. This is just the plot of the penetration of the clouds or water vapor. But of course, if you have some sort of atmospheric effects, you have a delay of your signal, INSAR signal. So since you are measuring you are counting the cycles which are related to the velocity of our wavelength, the velocity of light, passing through, if our signal passes through the clouds, it gets delayed. So we have to correct with this. In fact, we are doing atmospheric correction based on, in this case, ERA5 data. So it's another satellite data which capture the water vapor content in each date of our images and correct for that. Or we can use other different approaches to correct your.
So you're telling me that correction is basically perfect. I mean, if you're getting sort of rate. Then it would have to be perfect, and now you're telling me it's not. So are these rates that you're reporting to us that you can resolve? I mean, is that true?
What do you mean? I mean, there's an error related to the.
I mean, you're saying that you can resolve things at a millimeter a year or less, and then and it's an imperfect atmospheric correction. So
well, we correct for atmosphere, but of course there is always some sort of error related to the whatever it happens during the processing. So overall, the general error we can get is around a few millimeters per year. Let's say, depending on the target, between 1 and 2 millimeters per year, 3 millimeters per year of error related to the velocity. This is from experience, for what I found over the years. So everything is not perfect, and there are many components that you have to take into account for each pixel. So you can have a general idea what's your error. If you want to go into detail, you need a benchmark. So you need some very high precise information on the ground to compare your results. But it's better than, for example, LiDAR data. That it has 15 centimeters of error. So if you can 15 centimeters with 2 millimeters, it's like it's a good comparison.
Yeah. Okay. Thanks.
Welcome.
Colleen, I think I'm good. I mean, the only comment I have is that I think this is cool to see, and I think over the course of the workshops and all the things that we've seen, I think you can really, I at least feel like I can really start to imagine how combining these new tools in different ways to answer some of these questions will certainly help with sort of some key study designs for things going forward, right? There's a lot of opportunities to start integrating.
I think we can also combine the different projects together to have a better overview.
Yeah, so that's cool. Thanks again, Simone.
You're welcome, thanks.
Great, thank you so much, panel. Jump over to the chat now and read a few questions that have come in. This first one from Irv Mendelson. Your data show wetlands in the southeast corner of the western lobe of Lake Bourne with subsidence rates of about 30 millimeters per year. How can these wetlands still remain viable? Is their absolute elevation unusually high, providing them elevation capital?
I don't know. I mean, I don't know if the absolute elevation of the wetland remains high. I have no idea. Probably depends on the water level also. If the water level remains stable, but generally there's an increase of water level generally. So I don't know. I don't know if anyone from the panel can help me with this. Maybe not.
Simone, this is Mead. Can you at least zoom in on the section that Irv is talking about? So
yeah, sure. I made. That's here. Let me see. Here. It's right, I guess.
That's it right there.
Yep.
Mm-hmm.
And I'm talking about east of, northeast of the MRGO.
Mm-hmm.
That area very with purple and reds, yeah, right there, exactly.
Yep.
And if you look at that area on Google Earth, it's fairly intact. Not a lot of what would normally be thought of as subsidence-induced pond formation, although there are a lot of channels in there, what seem to be natural channels. But, with 30 millimeters a year subsidence rate between those two dates, what was it, 2006 to 2010, I wouldn't expect any of those wetlands to be viable, to be a subaerial. So it makes me wonder about the rates that.
Yeah, I don't know which is the height of the wetland there. For example, I don't know if you have any sort of range. I don't know if I know it's a wetland, so it's at sea level, but maybe it can be 50 centimeters, 1 meter high.
Yeah, if it received some materials from the dredging of the MRGO or overwash from Lake Bourne, that may all have increased the elevation some. But there may be LiDAR, I'm sure there is LiDAR data that might speak to that. Anyway, I just think those are the kinds of things one has to reconcile.
Yeah, of course. Yeah, that's an interesting question. I don't know if Mead can add something.
Yeah, I mean, I would just say we've had exactly the same thought, Irv. It's the last 4 years of data, right? And so that's 12 centimeters in 4 years. These marshes are not very high. So either we're going to start to see a quick disappearance of these marshes, or we've got something in error. So the first thing we did was reach out to the levee board folks to try and get a sense of what kind of on the ground RTK survey data they had, to at least along the flood walls, to give us some idea whether this is a realistic value. Because we're showing you preliminary data, right? We're not sure yet that what we're seeing is something we'd want to publish. And so that, unfortunately, that exercise with Carol's help, getting the data, resulted in even more complication, in the sense that they came back and said, well, look, we've got 5 different entities monitoring these flood walls. They're not going out at the same time and monitoring flood walls. In some cases, we've only monitored them once since they were built in the last 15 years. And we're going back and in real time, if we see sections of flood wall that are being monitored regularly that are going down, and the adjacent levee is going down, we pile soil on top of it again. Well, can we get a hold of the dates that you did that and how much? Well, we haven't gotten there yet either. So using this as an area to calibrate, which is our intention from the beginning, has started to turn up a lot of complications about just, what's a real rate out here and what's an engineering rate.
Yeah, I appreciate that. Thanks, Mead.
So I would just want to add something. For example, we collected some data from the CRMS survey, and this is actually the total surface elevation change rate in millimeters per year, which is based on the local, measurement on the wetland itself, and it shows like 1 centimeter at maximum in this case. Mm-hmm. So maybe it's not 3 centimeters per year as shown by INSAR, but it's like around 1 centimeter per year, which is still a lot. So I don't know how well the wetland will cope with these subsidence rates, or why we see such subsidence rates in the wetland, and why the wetland is still there. But yeah, this is what the data are showing, just to give you some more numbers.
Right. Thank you.
Great, thanks Irv, and thanks Mead for chiming in there as well. We have a sort of comment and question here from Chris McClendon. I am a collaborator on the Wells to Monuments program proposal. We have recommended using deeply anchored oil wells as monuments. These would be co-located with shallow anchored monuments. We have recommended that this apparatus be equipped with both GPS and INSAR reflectors. What do you think of this concept?
I think it would be great. Well, let me check again. So you are using deeply anchored oil wells, shallow anchor monuments. So basically, so they are deeply anchored, but you are measuring. Well, I don't understand why you said that they are deeply anchored and then you are related to the shallow anchored monuments. Can you give me some more details about that? Anyway, I think it's a great thing to have both GPS, to have the calibration, and also the INSAR reflector, which will give you a very high, very good reflector to work with. So probably it's the best approach you can get, and I guess it's quite cheap from the INSAR point of view. The GPS is a bit more expensive, but it's feasible. And also you have to consider the spatial distribution of these points. Of course, the closest they are to each other, the best it is, but it depends on the technical feasibility of the project and also on the budget, I guess. But I think it's will be great, because you can, as I said, for example, with this satellite, you have information, you have data every 12 days. Well, okay, since we have information every 12 days, and if you start building something today, you need at least 2 years of data to work with INSAR. So basically, you cannot process data just right now. You have to wait to acquire information over that area, which is covered by your reflectors, and then you can process the data and then obtain some information. So it's like a long-term project. But anyway, it's like probably it's a great solution.
This is Mead again. Can I add something to that?
Yep.
Actually, let me start my video here. So it's kind of rude to talk to people and not be on video. I was just going to say, one of the things we have thought about that goes to Liz's earlier question is that the wetlands are littered with all of this oil and gas infrastructure, platforms, pipelines, all kinds of things like that. And some of these are fairly large reflective targets. But you then go down the rabbit hole of how deeply foundationed are all these different structures. So that is one rabbit hole we do plan to go down. If we get down the road and we decide that the coherence thing is just too intractable in open wetland areas, there are some backup plans for how we can get spot measurements that might help us spatially. And of course, I agree that if you outfitted these things, if you tied them to a deep well and put a GPS on it and had a background stable value that you could use, it would be beneficial.
Great, thanks. One more question here from Dennis Lambert. Once a mosaic of different subsidence rates are accurately mapped out over the coastal plain, what is next? In other words, we know we are sinking and have known that. Is the solution on the restoration side to stack more material on these high-risk areas, inducing more subsidence, whether through marsh creation diversions, or is the solution to build more coastal protection systems to protect us as we are situated within the subsiding land? I am curious of the views because having made the mistake of building in this land and levying the river, we have to find a reasonable way to remain without creating more problems.
Well,
Krista, you want to chime in there too?
My video pops up when I hear myself being summoned. Yeah, so I think as far as CPRA and the master plan goes in particular, the goal is to incorporate the best available substance information into our modeling efforts, which then through that process would help with the prioritization of the state's projects that they're looking for implementing over the kind of 50-year window that we plan on. So essentially, I can't give you the answer of what it would mean in terms of like this restoration project versus this protection project, but we can say that that information would then be utilized to feed into the modeling effort that would then help us to prioritize those projects. So it wouldn't be a direct response to any particular subsidence numbers in isolation. It would be as part of that broader effort.
Thanks, Krista. I think that's a nice note to sort of end on today as well. So I want to thank again Dr. Simone Fiaschi for a great presentation this morning. Thank you again to our panelists, who have joined us now for 3 of these workshops. Thank you to the speakers earlier this week, Dr. Frank Tsai and Dr. Julie Bernier. Thank you again to all of the speakers who joined us for the first 2 workshops at UNO that were held. I want to sort of turn it over, back over to Diana to give sort of everyone a little bit of context on where we go from here, and to provide some sort of final closing comments before we let everyone go enjoy the rest of their Friday.
Thanks, Colleen. Yeah, I'd also like to thank all the speakers that we've had, since last December, from the first workshop through all the way through this last one. This is the last planned workshop of the series. So I'd also like to thank all of our panelists for joining us on all of these, and all the people who have attended the workshops. I know a lot of you have been with us since the first one. So thanks for sticking with us and asking some great questions. There is going to be a report from the panel in the coming months, probably later this fall. And that will just sort of be a summary of sort of all the information here, along with like some panel recommendations, some responses to those charged to the panel questions. So that's something we'll be working on in concert with CPRA, and so you can look for that to come out sometime in the fall. So again, thanks everybody for coming, and if there's anything that anyone from CPRA wanted to say before we close out.
Hi everybody, yeah, this is Carol. I just kind of wanted to echo all the thanks. CPRA has certainly enjoyed these workshops. They've been very informational and helpful to us. Thanks again, obviously, to the participants and the speakers, and a definite huge thanks to the panel. And we might not be seeing you much anymore, but we're looking forward to getting your work, and we know there's still going to be interaction until the fall. So just want everybody to know that the efforts are really appreciated, and that I've really been quite impressed with how the panel has gotten into the information, and it's just been a really, really productive experience for both me and CPRA. So thanks everyone. Krista, you have anything you want to say?
I think that summed it up nicely. I just want to say again, thanks to everyone who's been involved, and we really appreciate all the effort and time that y'all are putting into this, and we really do look forward to hearing what comes out in the report. So yeah, thank you everyone.
Great, thanks. So with that, we'll just close it out. So bye everyone.
Bye, everyone have a good weekend.